basically fourth problem on the assignment for today, but not everybody did it. I'll give that a midterm. They were probably concentrating on. But we maybe just didn't get to it. But this is important stuff. Okay, so here's an exponential function. Exponential function is a number to a power. Basic exponential function, the toolkit exponential function is 2 to the x. Okay. And you take a multiple of 2 to the x, that means you vertically stretch it. Okay. And if you add or subtract a number to x, that's going to horizontally shift it. And you're going to change it. This is not 2 to the x, it's 1.23 to the x. It still has a graph that looks just like the graph of 2 to the x, except for the labeling of the axes. And we'll see that in a minute. So anyhow, growth factor. Well, what is it that determines how fast this thing grows? What number is it that makes it grow? What number would you change if you want this to grow faster? Well, that would be this number. Now we've seen the graph of 2 to the x and the graph of 3 to the x. The graph of 3 to the x grows much faster than the graph of 2 to the x because 3 is bigger than 2. You're taking higher and higher powers of 3 rather than higher and higher powers of 2. 1.23 is a lot less than 2, so this is not going to grow nearly as fast as 2 to the x, but it's still going to grow. It's still going to have a graph that is indistinguishable from the graph of 2 to the x, at least until you look at the scale. Okay, and we'll see what I mean by that. Okay, so the growth factor is 1.23. Makes it grow more slowly than 2 to the x or 3 to the x. Growth rate 0.23 or 23%. Every time x changes by 1, f of x gets 23% bigger. If you invest money at 5%, which is a pretty good percentage. Invest money at 5%, then the growth rate is 5%, which is 0.05. It's not a rate of change. Growth rate and a rate of change both use the word rate, but they mean completely different things. They're related, but they mean different things. If you have 5% interest, and every year, it's annual interest, every year, you add 5% to what you've got, 5% of what you've got, which means you multiply by 1.05. So that the 1 in your growth factor means you get to keep the money that you have in there. And the 0.23 says you get to add 23%. If it's compound interest, compounded annually, you got $1,000 in your account. Then at the end of the year, you still have that $1,000, but you add 5%, which would be $50. And you have $1,050. So in the next year, you add another 5%. I think we've seen this in the process. Okay, so anyhow, it's really important to understand this. I mean, for your personal financial future, it's important to understand this for a lot of applications. And you're going to see, if you're, it depends what class you're in. My class, your assignment for today was to get a bunch of problems that related to why exponential functions are important. Okay. In other classes, you're probably going to see applications as well and get a good idea of why exponential functions are so very important. Okay, so anyhow, there's a growth factor and there's a growth rate. Initial value. You just plug in x equals 0 and you get your initial value. Show me with your fingers what 1.23 to the 0 is. Oh, any number to 0 times equal. So that's equal to 40. Now, what's that tell us about the graph? Well, if you sketch the exponential shape, and here in my class, we have detailed structure this thing, and if anybody else is interested, I can tell you what it looks. Just do this. Basically, you divide the thing in half with the vertical line down the middle, and then divide each half in half, the vertical line down the middle of that half. Horizontal lines from the top go halfway to the bottom, which gives you this. Then you go halfway to the bottom again, which gives you this line. Then halfway again, and halfway again. So if that's a pretty simple thing. If you go back and listen to what I said, write it out, and get it. Anyhow, you have this, 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 and this. There are your points. Well, if we're graphing this function, and you want to put the y-axis, several places my chalk tends to accumulate. These things anyhow. Okay. So we can put y-axis here. Now, we could put the y-axis any place we want, although for my class, for the toolkit exponential function, you're going to put it in the middle. You're going to have a red dot there. And you know about that. If you're not in my class, you don't know what I'm talking about it. Okay. But you can put the axes like this. Okay. And you can observe that every time you move over one vertical line, you double the value of the function, because each line is twice as far from the bottom as the one before. And that's because we went halfway here to get here, halfway from here to here is here, and so forth. A halfway construction gives us a constant doubling time. Okay. Now, as it applies to this function, the initial value is 40. So this line here is the line . I said nearly enough room. I wanted to get it on the same board. Okay, so this is a line y equals 40. And means the coordinates at this point are 0, x is 0 on the y-axis, and 40. Now, you don't know how to put a scale on the x-axis. Okay. But roughly, the scale for this thing okay, for this function f of x doubles if x increases by maybe because I'm doing this by middle estimate 3.4. You can actually calculate this doubling if you take the log of 2 divided by the log of 1.23. You do that with your calculator. The log of 2 is roughly 0.7. So if you took 0.7 and divided by the log of 1.23 using the log function of the calculator, it will tell you how closely I estimated that. Okay, it's fairly easy. 1.2 squared is 1.44. 1.44 squared is a little more than 2. So it's going to be less than 4. Okay, explain the details of that. If anybody wants me to write them out, just email. Okay. And 1.23 is a little bigger than 1.2, so I'm not guessing between 3 and 4. There's a rule of 72, a rule of 70. 23 goes into 70 about 3 times. That would tend to say it's 3. We're going to see that stuff, but that's coming up. Now, my point is that this graph now has a doubling time of about 3.4, so that this line here would be x equals 3.4. That means this line would be x equals 6.8. Point now is there's a way to calculate this doubling time so that you can label the curve. It's always constructed the way I constructed it. In any rectangle you want. So you can spread it out, make it thin, okay? And you're going to get a graph of that function. To the extent that 3.4 is accurate, then there's our graph. If I want to estimate the value when x equals 5, what's 5? Well, 5 is a little less than halfway between 3.4 and 6.8. So I could sketch a line, call it x equals 5, a little less than halfway. Put a little question mark there. Is it really x equals 5? There's my point. Here's my value. Y would equal F of 5. If if you've got something that's growing at a 23% rate every day or every month or every year or whatever, it's not money because you're not going to get a 23% rate on any kind of a safe investment. Okay. But if something is growing at a 23% rate, like you got a fish pond and every month the population increases by 23%, then you can make a good estimate just from this graph. How many fish you'll have after 5 months. Okay. Now, I haven't done the vertical scale, but the vertical scale is implicit. I mean, there's 40. So here's 80. Here's 160, right? So between 80 and 160, looks like it's about 110. Okay, so if you got 40 fish, 5 months later, they're growing at 23%. I just estimated from a graph that you're going to have about 110 fish. The graph is probably as good as your calculator if you can make a decent graph, and it doesn't take much to make a decent graph. And it allows you to just visualize how that population is going to grow, so you know when you're going to need to dig a bigger pond, okay, or whatever. So you're going to be able to estimate how much fish food to buy. Okay, you want to stockpile this stuff for a year, you want to have it on hand. All kinds of decisions that you can make for a function like this. Okay. Maybe it's the rate bacteria are growing in your refrigerator, because your refrigerator is quite as cold as it ought to be. Okay. And right here is death. Okay. If you eat it, you die. Okay. Here, if you eat it, you're going to get pretty sick. Okay. Down here, if you eat it, you're probably okay. Process that much, you might have a few digestive issues. It won't be much different than usual digestive issues. Okay. You can think about what those issues might be. I don't want to get into that. Okay. Makes sense? Yeah, you look, this is what exponential functions do. And you start understanding them by understanding the initial value, the growth rate, and the growth factor. You multiply the growth factor by itself a bunch of times until you get 2, that's your doubling time, approximately. Okay. You calculate log 2 over log your growth factor, and that tells you what your doubling time is. Okay. Okay. Well, that all comes off of problem 4 when they assignment that only one person did. But do it. You know, this assignment is very foundational, very. I don't know what I'm looking for. It's real important. You need to do it. Do it late. I'll probably, if you do it late on the half credit page, probably give you full credit through the end of the week because of most of the class having a midterm this week. Okay. Give you a little extra time to get that done. All right, now there's another thing that we can do. Let's take the fish pond model. Here's population P. This is time T in months. Here are 2 points in the graph. Okay. somebody show me, this is gonna be less than 10, some number between 5 and 10. Show me with your fingers a number between 5 and 10. Anyway, just hold up at least 5 fingers. Okay, I'm seeing seven, I see another 7, I see a 6. I'm gonna go with 7, because I don't want to do 6 and 2/3. Okay? You're gonna want to do 6 and 2/3. The vertical line is t equals 6. Well, now if this is 6, how much is this? It takes 1, 2, almost 3 of these, so let's just 10. Let's see this. It's reasonable. Okay. Now, how many fish should you have in your pond at this point? Now, you don't have enough fingers, you're gonna have a lot of fish. But somebody held up 6. And we did, wait a minute. I'm gonna use 6, and I apologize to people who said 7. Okay, but those of you who said 7, I'm gonna use your number. We're gonna multiply by 10. Let's say we have 70 fish here, right? Now this is a little less than half of 7. I'm gonna say here we have, let's say here we have, it's not t equals 70, this is t equals 70. T equals 25. Okay. Now, you know what an exponential curve looks like? We just drew one. I'll draw one. Here, it kind of looks like this. Might be more parabolic than exponential, but that's all right. Okay, but I want you to draw an exponential curve through these points. Have a copy of that, label it, sketch an exponential curve as best you understand the shape of an exponential curve. Okay, now everybody do this exercise. Estimated the population when t equals 4. Of course, there's a line when t equals 4. Everybody got the same estimate. Nobody's sitting close enough to even read other people's minds. Okay. So I know that didn't happen. There's something going on. The gremlins are in or whatever. Because everybody got 45. And that's pretty close because the actual estimate that I make is 44.993. Okay. So y'all done good. Well, actually, 45 makes perfect sense to me as well. So I'll accept your estimate because I don't think I can prove it. P equals 45. Now we're going to be able to figure out what P really is. Okay. If you have an exponential function that goes through these 2 points, because any exponential function A times B to the T. The exponential function can be expressed in the form y equals A times B raised to the T power. So what do we know? Well, here we have P instead of Y. use P equals A times B to the T. Now, just as on the function that we started with, 40 times 1.23 to the X. Okay, this has a number times some number to the T power. I didn't use X, I used T because very commonly exponential functions are time variant functions. Okay, they can also vary with position X, but I'm going to use T typically. Okay, so what do we know? Well, when T equals 2, what's the value of T? 7, right? T equals 6, what's the value of T? I'm sorry, T equals 2, the value is 25. When T equals 6, the value is 70, right? So we can take our information P equals 25, if T equals 2, P equals 70, if T equals 6, then we'll have this kind of information anytime we have 2 points on the graph. Put this information into the form, E equals A times B to the T. Yeah, what? Well, if you put 25 in for P and 2 for T, what do you have? Replace P by 25 and T by 2. Write it out. Okay, now everybody got this very quickly. First set of information, you get 25 equals A times B second, and the next, get your 70 equals A times B to the 6th. Okay. Now we want to solve these equations. This is 2 equations. And the 2 parameters A and B. We've got 2 equations and 2 parameters. We can solve them simultaneously. Now, how do we solve these equations simultaneously? Well, how about this? Can you solve the first equation for A? Okay. So I'll use a circle 1 and a circle 2 to refer to these 2 equations. Instead of solving first equation, it's easy to just write solve circle 1 for that. Well, you're going to get A equals 25 over B squared. Now everybody showed me enough algebra. Everybody's either got this or solve for B and got something even more complicated. Okay, square root of 25 over A. And either way is going to be fine. Okay, but since I said solve for A, we're going to do that. Okay, so now plug I'll just say plug this into equation two. In other words, A is this, so now A in equation two. You get 70 equals 25 over b squared multiplied by b to the sixth. Okay. Now see if you can solve that for b. You do have an equation here that you can solve for b. I'm going to see what you do with it. I'm not going to let you twist in the wind too long if you don't know what to do. But let's see if you can do that. Okay, a couple of side notes here. There's a couple of errors that I see people making. I'm going to have to write a pretty small one here. But to solve this equation for A, you got to divide by b squared to get the A, and you get this. So the A equals 25 over b squared. And you really want to write out those steps to reinforce something that I don't think anybody at this stage is likely to be all that. I don't think anybody at this stage has a complete grasp of these rules. Okay. You want to keep reinforcing them so you'll develop a complete grasp. Because you pretty much have to be able to do this automatically. Okay. So you want to develop that. Now, over here, what's 25 times b to the sixth over b squared? Well, you see b to the sixth over b squared, you think a times b times b times b times b times b divided by b times b. You think that because people are still making a whole lot of mistakes with the rules of exponents, and you really have to get over that. Okay. And if you do this, you see that, well, two of these b's here, two of these b's. These divide this, gives you one, leaves you four b's, which is b to the fourth. I dislike cancellation because people do it wrong. Because people don't know the rules for cancellation anymore than they know the rules for exponents. Okay, kind of know them, kind of familiar, but it's real easy when you see division here, here, to divide the two into the sixth. And that makes no sense at all if you think of what b to the sixth and b squared mean, but it's an easy mistake to make. Okay. And the way you learn things is by making a lot of mistakes and checking yourself, and finding that you made a mistake and deciding you don't want to make that mistake anymore. All right. So anyhow, you get 25 b to the fourth equals 70, don't you? Okay. Can you solve that for b? Well, you divide both sides by 25. I put three dots there to indicate that that's a step you should write on it. You get b to the fourth equals 70 over 25. Okay. Now, does anybody want to tell me how you solve that for b? Okay, so you know, I just said one reason we got this support course is so that I can include explanations of things like this. I'm going to write out the solution, and then I'm going to find some space somewhere on the board to explain the solution. But what we do is b to the fourth raised to the 1/4 Well, if you raise a power to a power, you multiply the powers. 4 times 1/4 is 1. So we get b to the 1, which is just b. But now b equals, and there are a bunch of steps. It's going to be 70 over 25 raised to the 1/4 power. Now, if you want to put that into your calculator, you can divide the 25 into 7 if you want, but you don't really have to. 70 over 25 raised to the 1/4. Now, I'll estimate that that's about 2.8. And square root of 2.8 is 1.4. And the square root of that is a little over 1 point, a little under 1.2. It would be 1.18 or 1.19. So I'm just going to take a stab and say 1.18. And I just put it in my head, which back so I said 1.18. Okay. So I think I've got that right. All right. Well, what's the outcome of this now? What outcome is it? And so approximately is a times 1.18 to the t. Now, what can we do with that? We can go to either of these equations, plug in b equals 1.18, and solve for a. Now I'm going to say do this one. Plug b equals 1.18 into equation 1. See what you get. Okay, now what we need to do, here's equation 1. How do you solve for a? Well, a is multiplied by this. If you want to get a by itself, so you better divide both sides by this. Okay, I should have warned you to restrain your left hand, because as soon as I say that, the typical response is, oh, okay, and I don't want anybody coming out. Okay, so we have now write this stuff out. People are leaving things out. You haven't necessarily shown the step where you divide both sides by 1.18 squared. Yeah, partly because you're not sure what to do with that 1.18 squared, but that's easy. I'll tell you in a minute. Okay, it's just there. It's something that's multiplied by 8, so we divide both sides by it. Okay, and we get a equals 25 to 1.18 squared. Okay, that's approximately equal to At this point, you just plug that into your calculator. I don't expect you to be able to square 1.18 in your head, but it's actually fairly easy to do that if you know your multiplication. Yeah, I think you get 1.394, which is very close to 1.4. And as it turns out, you get 1.461 if you do 1.19 squared. So so that's 140.6. This is 139.4. 1.4 is almost exactly halfway between 1.18 squared and 1.19 squared. Okay. So you need some more decimal places to get this more accurate. And this then is approximately 25 divided by 1.14, which is a whole lot like 25 times 0.7, which is ballpark 17. Okay, it would actually be like 17, but a little bigger down. Might be closer to 18. I'm going to guess 17.6. So A equals AB to the T. And AB equals 17.6. I could be off. Don't trust my mental arithmetic. Okay, 17.6 equals 1.18. Finally, P, and I'm going to write it as a function out, P of T equals 17.6 times 1.18 to the T. So kind of make sure you understand how we solve this once you got to 1.1. There's your function. Now remember, we estimated if T equals 4, population ought to be 45. Therefore, 17.6 times 1.18 is 4. That's not going to come out that close. Maybe I made a mistake in some of these numbers. Now kind of close to 35, but that doesn't make any sense. So chances are I did something boneheaded with some of these numbers. Doubling time ought to be about 4 years. More than no, it's just something's wrong. The process is correct. I must have made a wrong estimate at some point. And I think I see where it is. Yes. I 1/4 power is what I got excited because that's pretty close to 2 times the square root of 2. So 1.18 was off. Pretty sure it's closer to 1.3, and of course that would affect all the other numbers. Another thing that's wrong with this model is when t equals 0, it looks like p is about 10 or even a little less. So if we had to put 1.3 in here and divided it into 25, well, would have come out that close to 10, but remember that's not very accurate exponential. Okay. Process is, as I say, but here. That's not X, that means that's wrong. Use calculator, you won't make those mistakes. The other thing I'll wrap up with is this one fourth power. So /70 over 25, I messed it up. V to the fourth is 1/4 equals 70 over 25 to 1/4. That means V to the 4 times 1/4 equals 70 over 25 1/4. And 4 times 1/4 is V to the 1. That's another thing you really need to work to understand. Laws of exponents says a to the b raised to the c is a to the b times c. The 1/4 power of a 4th power, you multiply the 4 by the 1/4, you get this. And I think everybody really needs to do some work on the rules of exponents, because you'll stumble. And I'll try to remember, and if I don't remember, email me and ask me to remember to post a link to some videos on rules of exponents. But of course, you can go out and find 48 million good videos on rules of exponents, okay? Find all kinds of explanations, find one that makes sense to you, but make sure you not only think you understand the videos, but do about 100 problems. It only takes about 30 seconds to do a problem. 100 problems in less than an hour. Okay, and if you want problems, let me know, I'll send you some. But I'm not going to go to that trouble unless somebody's going to use it. Okay. Because you can find them. Yeah. Just look for them. I'll be glad to give you references and everything else if you need them. So let me know.